Part 1, linked above and in the description, we discussed why we charge our trailer batteries with a DC to DC charger while towing, and some of the issues with voltages, battery equalization, etc.
About a third of this video shows our installation, the basic configuration, and some very cool advanced arrangements that are valuable for a variety of Victron setups.
The rest is about our step-by-step safety considerations. Fair warning, it's a bit tedious. But we'll wrap it up with a summary. Our installation is specific to our 2025 nuCamp Tab 400 Boondock Black Canyon, our 2017 Audi Q7, and the Victron Energy Orion-TR Smart 18. And please note that we discuss the safety of this installation in great detail in the safety chapter of this video.
DC to DC chargers are often installed in the tow vehicle, and from there, big, beefy wires are run to the batteries in the trailer. The big and beefy wires are sized to carry the current with minimal loss, but also to minimize something called voltage drop.
Voltage drop occurs due to the resistance of the wire between the source of the power and an electrical component, as the electrical current flows through the circuit, losing some voltage due to heat generation. Voltage drop can be reduced by minimizing the resistance, and that is a function of wire thickness and length. For us, we chose an approach that can also be found in Airstream Tradewind trailers and optimizes the charging of the trailer battery. We minimized the voltage drop by having a short connection between the DC to DC charger and the trailer battery, and we accepted the voltage drop between the tow vehicle and the charger.
We also used the existing wire in our trailer and tow vehicle. That decision required some deep research to ensure the safety of our setup. Please see the safety chapter in this video for that.
In our Tab 400, the 7-pin wiring is routed from the plug to a junction box near the front of the trailer, and from there into a space underneath the galley, where the charge and ground wires connect to the power distribution panel.
We started our installation by A, making sure our 7-pin was not plugged in, and B, turning the trailer's battery switch off. The lack of interior lights made for poor photography. Sorry.
To get to our installation location, remove the drawer directly above the power distribution center. This will reveal an access panel. Remove the 4 screws holding it in place, and the space underneath can be accessed.
We opened the junction box behind the spare tire and found that nuCamp used red and white 10-gauge wires to extend the charge and ground wires from the 7-pin harness to the power distribution panel. After disconnecting the wires from the panel, we tested them to make sure that what we saw emerge in our installation space were indeed the 7-pin charge and ground wires.
We routed those wires to the in ports of the DC to DC charger and ran new wires from the charger's out connectors to the distribution panel. We plugged in our tow vehicle and the 7-pin supplied power to the charger. With the engine off, we configured the DC to DC charger, turned the battery switch on, and then started the car.
It all worked as expected, so let's look at the configuration next. Touch on the device in your list. Touch the gear icon in the upper right-hand corner. Touch battery settings. The maximum absorption time is 30 minutes per battery. Adjust this figure if you do not have 4 Battleborn batteries.
We had lowered the absorption voltage to avoid a clash between the DC to DC charger and the solar charge controller. We'll explain a better way to avoid conflict between Victron chargers in the next chapter. Back to 14.6 volts, which is what we like to use for Battleborn lithium-ion batteries.
Next, engine shutdown detection.
These settings work, but the shutdown of the charger occurs after the tow vehicle's output has dropped below the shutoff voltage for 1 minute. We want the charger to stop as soon as the alternator is stopped. For that, we can use the input voltage lockout.
With the engine running, we saw the input voltage fluctuate between 13.04 and 13.15 volts. The moment the tow vehicle's alternator stops, our voltage will drop to 12.8 volts or less, and the DC to DC charger will stop. It will restart at 13.1 volts, a voltage we can only reach when our alternator is running. And with that, we slipped into advanced settings. The advanced settings require very little and will make a lot of sense if you watch the earlier parts of this video. We recommend them to everyone with this or a similar Victron setup.
In the last video, or part 1, we shared our opinion that relying on voltages alone is error-prone. We also recommended that you get a shunt, as a shunt will give you much more usable information. The same is true for systems working with other systems.
As it turns out, our system has a shunt, and by default, our Victron equipment does not use it.
Let's change that. We already have everything we need. There is no additional cost. All we have to do is use the built-in Bluetooth networking to allow our components to exchange their data.
Let's start with the shunt's configuration. Touch on the device in your list. Now touch the gear icon in the upper right-hand corner. Select VE Smart Networking.
Since we don't have a network yet, let's set one up. You can name it anything you want and don't have to remember the name.
Touch OK.
Going forward, the shunt will transmit the voltage of the battery bank and the current going in or out of it to all devices on this network that can receive it. Those devices are no longer led astray by random voltages from devices they know nothing about.
Now let's add our other devices, and we'll explain some additional benefits we will get.
This time, choose Join Existing, then select the network we just created.
The solar charger will now use the exact voltage from the shunt instead of allowing itself to be fooled by the DC to DC charger.
If you add more than one solar charge controller, the controllers will now elect a primary that manages their interactions. No more stepping on one another.
We are joining all of our devices to the network. The Multiplus will provide its voltage and the temperature. The temperature will allow all chargers in the network to optimize their charging profiles.
And this is where we wished we had spent the extra money on the newer Orion XS charger. It supports the networking, and our older Orion-TR does not. Our DC to DC charger will charge as before, but at least our solar controller can now optimize its contribution and avoid conflict due to the Orion's voltage. If you have been watching our videos, you know that we don't ask to like and subscribe, and we don't try to drive viewer engagement by asking you to comment, but we are asking now that you add your thoughts to the comment section if you think we missed something or got something wrong in this chapter.
Or in any of the other chapters, for that matter.
We think that we have carefully considered all of the risks from end to end and will review them here. The distribution panel, wiring, fuses, junction boxes, connectors, more fuses and wiring, and of course the batteries and the alternator.
But first, let's see what the impacts of the device itself are.
We can see that the output is 220 watts or 18 amps at its nominal voltage of 12.2 volts. For the generation of electricity, and this is true for solar panels, alternators, etc., cooler is better. The specifications indicate that the device will produce 220 watts continuously at 40 degrees Celsius or 104 degrees Fahrenheit. This will be the device's temperature, not ambient temperature.
As the temperature climbs higher, the output is derated by 3% for each degree. We could increase ventilation if we don't want that, but our concern is to keep output low, not high.
At 25 degrees Celsius or 77 degrees Fahrenheit, the Orion-TR outperforms its advertised values and will produce 280 watts. But it can also surge to 25 amps for 10 seconds. At its nominal voltage of 12.2 volts, that would be 305.55 watts.
The newer Orion XS is 98.5% efficient and runs cool. Our Orion-TR shows its age with an efficiency of 87%. It needs to consume substantially more power to produce its rated outputs.
We are interested in the currents at our operating voltages of 13 to 13.1 volts in and 13.5 to 13.6 out. Most of these currents are higher than we thought they would be, and we will have to take a cautious and meticulous look at what this means for our setup.
There may be concerns about leaving the tow vehicle plugged into the trailer over an entire camping weekend. The device has a standby current of 1 milliamp, meaning over the course of 72 hours, we would consume 0.072 amp-hours from our 95 amp-hour car battery.
The device itself causes no concerns. Its higher than expected current may have effects elsewhere that we will keep in mind.
On its 12-volt side, the power distribution panel is designed for power inputs of up to 75 amps and has space for 15 individual circuits, 3 30-amp and 12 20-amp circuits. Our DC-to-DC charger will pose no threat at all.
Next up are the battery disconnect and the glow-so fuse that protects the power distribution panel. The disconnect switch is rated at 275 amps because it has to handle everything going into and coming out of our 4 lithium-ion batteries. The glow-so fuse, or circuit breaker, is rated at 40 amps. Both are well beyond the maximum we can expect from our DC-to-DC charger.
We are not worried about these two components. Let's also look at the wiring involved. The battery cables are beefy, designed to deal with 200 amps of current when supplying our multi-plus charger inverter. And even the wiring to and from the glow-so circuit breaker is far more substantial at a 6 or 4 gauge. We are not worried about these thick wires overheating.
It probably goes without saying, but our 4 battle-born lithium-ion batteries handle this charging current with ease. Together they can be charged at 200 amps, and while underway, the solar charger is the only other contributor with a theoretical maximum output of 50 amps. So far, we are not concerned about any of our components.
For the remaining item on the output side and to connect the DC-to-DC charger to the distribution panel, we used a 1-foot section of stranded marine tinned copper wire that is rated for 60 amps when used outside and 51 amps inside of engine spaces, substantially beyond our requirements and twice as much as automotive wire. Why marine wire? Because that's what we had.
Let's move on to the input side, and some low-hanging fruit there. We'll include wire considerations later and focus on the connector pins here. In particular, the pins for auxiliary power and ground are rated for 40 amps each per SAE J560. Worth noting is that the ground pin carries the current for all of the other pins combined, so we need to consider what else is going on.
The junction box on our nuCamp Tab 400 is simply holding a set of 7 posts that facilitate the joining of 2 or 3 ring terminals each. As long as those terminals are appropriately sized, everything is fine. We inspected ours when we installed the repeater for our tire pressure management system.
You may think that this step is unnecessary, and we shared that opinion until we saw this during another unrelated project. These ring terminals are much too large, and only a portion of them are making contact. That can easily become a fire hazard.
Our concerns for our starter battery were primarily around draining it too much. The DC-to-DC charger disconnects the trailer when the engine is off, uses almost no power itself when in standby, and our settings terminate the charging when the alternator drops too low or is turned off to reduce emissions while the engine is still running. The car's battery management system can also shed loads to protect the battery. One of these very large main fuses protects the electrical branch used by the charger, and should it draw too much, the fuse will blow, and the battery will still be okay. We are not worried about the battery or the wiring from this fuse to the fuse box it protects, but there is some risk to this fuse.
Similarly, we are not worried about the wiring from the alternator to the battery. It is designed to handle the full output of the alternator. Our concern is related to the alternator having to produce its output at lower engine speeds than normal, and thus not getting the cooling it gets at higher speeds. A 180 amp alternator cannot magically turn into a 250 amp version. The demands on the wire have not changed.
Let's explain next how we alleviated our concerns around the alternator.
Our thinking was informed by our experience with traditional alternators, like the one in Emerson. They always work hard, and adding an electrical load would mean that they had to work even harder. Smart alternators are part of a system that is centered around the battery. If the battery can handle the load, the alternator may not even come on until it is time to recharge. Our added load is significant, but so is the battery at 95 amp hours. When the trailer is plugged into our tow vehicle, tow mode is automatically activated, and as car and driver noticed in a review, the alternator will have a higher output. Instead of providing 322 watts at 13 volts and 25 amps, it would run at 14.7 volts and 22 amps. And it would probably run more often. The system is also capable of shedding non-essential loads like heated seats, infotainment, and charging through the 7-pin harness.
We may not get the charging we want, but we also won't get the overheating we feared. Today, we are no longer as concerned about our alternator as we were yesterday. At least it is no longer top of mind.
The electrical system of our 2017 Audi Q7 has a fuse panel located in the cargo area that serves, among other things, the 7-pin trailer harness. Judging by the open slots, it looks like it has capacity available. But rated at 160 amps, it already contains fuses totaling more than that. Let's have a closer look. nuCamp and our brake and axle manufacturer Dexter agree on the pinout of the harness, a crucial first step in translating Audi's fuse designation.
For loads over 3 hours, fuses should be rated to 125% of their load to prevent overheating according to the National Electrical Code. For all others, the ratings should be 150%. 2 of the slots are unassigned, and another 2 are used only in diesel models, which ours is not. The rear blower and rear climate controls are always on, even when we travel alone. The same goes for the amplifier. We never use the third row seat, and I'm tempted to remove the fuse. However, for now, we'll call it intermittent use.
The trailer lights left and right fuses support the turn signals, brake lights, and tail lights. They are rated at 125% in case we tow with our lights on. What Audi labels trailer hitch powers the trailer brakes. It intermittently uses 3 to 4 amps per brake or 6 to 8 amps in total, but has a 30 amp replacement fuse.
The trailer socket maps to the charge line we need for our DC to DC charger. It will always be on and is fused at 15 amps, bringing our total to 151 amps and under the 160 amp maximum.
The last 2 seem wrong and no longer have their original fuses. Industry standards, our brake manufacturer, Dexter, our brake controller manufacturer, Redarc, as well as the 7-pin harness manufacturer, agree that a 12-gauge wire should be used for the brakes. We also confirm that a 10-gauge wire is used for the charge line. The ampacity of wires depends on the length of the circuit, but for short runs it is 30 to 40 amps for 10-gauge and 20 to 25 amps for 12-gauge wires. The 30-amp fuse would not protect the brake wiring, and the 15-amp fuse would unnecessarily limit the charge line. We will have to dig deeper into this.
So we headed to our favorite Audi dealer located in Seattle's University District, and Brandon set us straight, looking up the factory fuses. And this is it, or rather these are them.
The maximum current that could flow through this fuse box could be as much as 209 amps. But it is important to recognize that only some of these loads are continuous. And for us, some are not there at all. That really matters. We are back to 151 amps total. The taillight fuses are oversized, and the third row seat fuse can be removed. We are confident that we can increase the charge line fuse to 30 amps. If we overstep, the main fuse will blow, and we'll make adjustments. But we'll start with 20, and next, we'll calculate what our wiring can safely handle.
Given what we learned here about the fuses and the overall budget of the fuse box, we are not worried about the box or the main fuse.
However, fuses protect the downstream wiring. We need to have a look at that first before we can safely increase the fuse size.
For us to understand how much current a wire run can safely carry, we need to consider a number of factors. We mentioned a couple already, and we'll touch on all of them next.
To determine if our wiring will be safe for our 20 or so amps, we need to consider the entire run. However, sections of our run are affected differently, so let's examine them separately as well. The baseline ampacity, or the amount of current a wire can safely handle, is determined primarily by the material, its insulation, and its size or gauge. The baseline is then derated depending on a conductor's interaction with other wires and has primarily to do with other wires in a bundle, allowing or restricting the dissipation of heat that electrical wires generate. And that, of course, has also to do with the heat generation by the rest of the bundle.
We have one never-used wire in the pigtail and then several wires that are only briefly and intermittently used. We can disregard those for our calculation. The wires serving the tail lights are sized for incandescent light bulbs and are thus rather generous for our LED lights, consuming only between 0.2 and 1 amp. We found that their heat generation in our bundles is negligible.
All of the wires considered here have a GPT insulation and are rated for 105 degrees Celsius and 40 amps. Pretty typical for automotive wiring. We found that most popular brands offer ratings from 33 to 38 amps. We'll go with the lowest number to be extra careful. For loose bundles, the base ampacity needs to be derated by 10%, and for tight bundles, 15%. It is important to recognize that the most restricted section sets the limit for the entire wire run. That is the pigtail. For our purposes, we will consider 28.1 amps to be the maximum current for our charge line.
When called upon, our alternator will run at approximately 14.7 volts. There are 3 reasons why our DC to DC charger may report a lower voltage. 1. Measurement issues, such as low-quality multimeters. Victron and Blue Sea are top-notch manufacturers of precision equipment. We don't think that is an issue for us. 2. The secret sauce in the DC to DC charger may step it down to a more palatable voltage. And 3. Physics. The resistance of the wire will reduce the voltage measured at the source to a lower voltage in proportion to the length of the wire and the current it carries. Let's figure out the voltage drop using the 12 amps we just saw in the screen recording and our limit of 28.1 amps from earlier in this chapter. At our low end of 12 amps, our voltage drops from 14.7 volts to 14.39 volts. And at our high end of 28.1 amps, our voltage would drop to just under 14 volts. As the current increases, efficiency drops while the temperature of the wires and the available power climb. Our DC to DC charger, depending on its own temperature, may require 253 or 322 watts and can surge to 351 watts, all below our maximum.
We are not worried about our wiring. Great news. Let's summarize. As you saw, our DC to DC charger is a touch too powerful to be considered a drop-in. For that, Redarc offers a couple of 12-amp models, one of which is used by Airstream in Tradewind trailers. Victron's newer XS model can be configured to limit its current and would also be a good fit. Staying within the Victron ecosystem, in particular with the Orion XS, allows all relevant components to share information on a Bluetooth network, which has a variety of benefits. We have to increase our fuse size and think we can safely do so. Notwithstanding the charging of our trailer batteries, the most significant benefit may be that the trailer battery and our car's starter battery are electrically separated when we are stopped, and the 7-pin harness is still plugged in. While even the maximum possible currents are safe, we will report back on our experience. We suspect that we will see smaller numbers. Had we read the detailed specifications first, we would have purchased the more expensive Orion XS, and that is the model we recommend. But every tow vehicle and trailer combination is different, and we are not professionals. We provided our detailed considerations to simply share our experience and suggest that you use a professional installer. Thank you for joining us.
Thank you.